Section 12.1 has really kind of been building up to this key topic here. Composition of functions is a pretty interesting topic in its own right. Inverses of functions has got some uses and is a pretty important topic in its own right. But we really need this topic here for what's happening in Chapter 12. So the most immediately useful thing from 12.1 is this stuff here. And what this is about is how a function's graph is related to the graph of its inverse function. So I'm going to grab a couple of the functions we were working with in the second video, the medium difficulty ones where we had two different things going on, and I'm going to graph them. And we're going to take a look and see how the graphs are related. So one of the functions we were working with in the second video was this one here. And if you look at that, you'll recognize, hey, that's a fairly easy thing to graph. Did that kind of thing back in Algebra 1. That's a straight line. It's got a y-intercept of 5, so let's see, 1, 2, 3, 4, 5 up there. It's got a slope of 3, so it's going to go through that point, and that point, and that point, and so on. I'll just go ahead and grab my ruler and connect the dots there. And there's the original function's graph. And then, for comparison, I'm going to graph its inverse, which, when we were working with it in the second video, it looked like that, but it'll be easier to graph if I break it up into two fractions. The two fractions are going to be 1/3 x minus 5/3. And the reason I think it's easier to graph that way is it looks like a straight line, doesn't it? So the y-intercept is a little awkward, negative 5/3. So 1, 2, 3, 4, 5/3 is down about there. And a slope of 1/3 means rise 1 and run 3, which would be up from there to that little fractional point and then over 3, and up from there and over 3 and so on. And I grab my ruler and I draw the dots. And then we need to talk about how those two graphs are related. And this is the thing that I've always found a little bit frustrating in most textbooks. And that is, the examples that you end up graphing, they're not very useful for understanding what the relationship is. Just like this example here. When you look at those two pictures and I say, what's the relationship? Your mind runs off in a million different directions. They're both straight lines. They both have positive slopes. You can think of probably 100 different things that are related about those two graphs. And the reason why this is a bad type of example to teach this from is because there's not much going on there. The graphs are kind of simple. They're just straight lines. Straight lines are kind of boring. They don't wiggle around any or do anything distinctive. So to try to figure out what the relationship is, you need something that's a little bit meatier. The other thing that's going on is you can't help but be distracted by the equations of these graphs. I want you to look at the graphs, and I want you to think about how the graphs are related, but your mind and your eye just keep drifting back to the left where the equations are, and it keeps distracting you from what you're supposed to be doing. So I'm going to work a second example that I think will do a better job of telling you how the graphs are related. And this example is going to be a little weird, but follow along with what we're doing. What we're going to do is we're going to graph a function and its inverse without knowing what the equation is, because I don't want you to be distracted by the equation. And the graph is going to be kind of a weird, wobbly, complicated graph because I want you to be able to see the structure of what's happening better. So the original function, all I'm going to give you is this table of values. Where did it come from? Don't know. Doesn't matter. I'm not going to tell you. Let's just plot the points. So negative 5, negative 4. 1, 2, 3, 4, 5. 1, 2, 3, 4 is down there. Negative 2, negative 3 is there. 0, 0, we know where that is. That's there. 1, 3 is up there. 4, 4 is there. And then 8, 5 is there. So with those 6 points, you can kind of see a sort of an S-curve looking thing that looks sort of like this. Passes the vertical line test, so yes, it's a function. It passes the horizontal line test, so it does have an inverse function. And we're feeling a little out of sorts because we didn't have an equation, but we still were able to draw the graph okay. Now here's the part that's going to be a little freaky. I want you to graph the inverse of that function. Well, you don't know what the equation is, so you're not going to be able to figure out what the inverse equation is. All you're going to be able to do is build a table of values of the inverse function. Well, how are you going to build a table of values? Here's how. Hold on a sec. Inverse function means that what used to be the output is now the input, and what used to be the input is now the output. So what that means is you switch the x's and y's. Used to be x was -5, y was -4, so now x is -4, y is -5. You switch the x's and y's, you switch the inputs and outputs, and that's how you create an inverse function for the equation. That's also how you create an inverse function for the table of values, for the points. So when I switch that one, 0, 0, it switches to 0, 0. That part's kind of boring. But the rest of these, when you switch them, they actually change into new and different. Well, this one doesn't change. 4, 4 switches to 4, 4. But most of them change to different points. So when I go to plot these points, let's see, -4, -5 is here. And just to help you remember, that point kind of moved over to there. It used to be -5, 4, now it's -4, -5. And -3, -2, this point here kind of moved up over there. And this one didn't move at all, stayed right where it was. 3, 1, that point there moved down over to there. 4, 4 sort of stayed where it was, and then 5, 8 is up there. This point sort of moved up over to there. And when I connect these purple dots, I get a picture that looks like this. Oops, missed that side. Let me try drawing that part again. There, that's a little better. And that's a much more complex picture. But the complexness of the picture helps you see what the relationship is. Look at the blue line, look at the purple line, and what's the relationship? The red arrows kind of help you see what the relationship is. It's a mirror image, it's a reflection. And it's a reflection in kind of a diagonal direction, where here, this is the mirror that everything is getting reflected through. All the blue points moved across this green line to become purple points. So this one moved over there, that one moved over there. The ones that were right on that line didn't move at all. This one moved over to there, that one moved over to there. So this is a much better picture for understanding how a graph and the inverse graph are related to each other. They're mirror images. So the general rule to draw out of this is that a graph and its inverse graph are mirror images across that diagonal line. So a function, its graph, and the graph of its inverse those graphs are mirror images across, well, how am I going to describe that line? That's a diagonal line. Well, a lot of lines are diagonal. It's the diagonal line that's exactly symmetric. Well, that doesn't help much. Well, if you take a look, that line has a really easy equation. It went through 0, 0, and it goes through 1, 1, and it goes through 2, 2, and 3, 3, and 4, 4, and 5, 5, and 6, 6, and -1, -1, etc., etc., etc. That green line there that is our line of symmetry, our mirror image line, that's the line y equals x. You can also say the 45-degree line or something like that, but y equals x is the equation of the line we do our mirror image through. This is going to be the most important thing out of section 12.1. Later in chapter 12, we're going to need to do this because we're going to be able to graph a function, but we won't know yet what the graph of the inverse looks like until we do this mirror imaging process. So we're going to use this as a tool in the future. Make sure you're pretty good at it.